So this is going back. I'm going to try and include some bell work that's not always just what we did the previous day, but all throughout what we've learned. Pretty straightforward question. If you have outliers, what's the best measure of central tendency and variability? And the best choice here is median and interquartile range, E. So if it is not, okay, well, maybe it's easiest to talk about mean and standard deviation. We use this when it is unimodal or uniform and symmetric. And those are the conditions for using this. If it is skewed, bimodal, multimodal, if it has outliers, remember your mean and standard deviation are affected by outliers. So if it has those things, then we want to use mean and interquartile range. It's kind of like the backup choice. All right, so E is the correct answer. Hopefully you are remembering that. All right, so we've got a few things to talk about. First of all, we've got some progress and some little bit of minutia to talk about, and then we're going to get into expected value. So we've got progress checks. So this, first of all, old progress checks. What this is running through right now is kind of some ways, because some of you might be worried about your grades currently, and I'm trying to give you guys some suggestions for things you can be doing to bring those grades up right now and things you can be thinking about for the next few weeks. So progress checks, turn in the old ones for full credit. Some of you have been doing those, so this doesn't apply to you. But some of you are sitting there with zeros for your progress checks. As soon as you get those done, it's full credit. I know it's a lot of multiple choice questions to sit through, but it's also a really good review. So if you have waited, it's going to be kind of a side benefit here is maybe looking back and saying, okay, now I'm remembering this old material. So make sure you go and do that, and that can bump your grade up pretty significantly if you haven't done any of them yet. Now this is also, so this is a suggestion from Sam, if you don't mind me saying, but these progress checks are really closely aligned with what your tests look like, the multiple choice at least. So I thought it was a good idea. What I've done is I've made unit 4. Now the units for AP don't match the AP, or the units that we're using in class, the numbers. But their unit 4 progress check is available for you. I unlocked it. And specifically parts B and C to that are things that we're going to be looking at, random variables and what we call the binomial and geometric distribution. So anyways, you can start looking at that stuff right now, and that's just going to help you realize what the test format might look like. So use it as review for your next test. And of course, when we get closer to it, you'll know how to approach those problems. Your homework. If you have not turned in old homeworks, and some people haven't turned in homeworks from, the second week of class. So if that's you and you haven't turned some stuff in, turn it in for half credit. That's better than a 0. And it's pretty simple to do. So these are, again, ways of bringing your grades up. And test retakes. So some of you already asked about test retakes, and I kind of earlier was telling you to hold off, wait until we've done some more tests, see if that's really what you want to do. But we're just 2.5 weeks from the quarter ending. So if you want to start thinking about scheduling your test retakes, maybe you hold off, until the next test to see how that one goes. But anyways, if you know there's one that you really want to retake, then you can start figuring out how to schedule that. And so the way that you do that is you could just email me and you could say, can I retake the unit 3 test? But you'll need to know what day you want to do that on. Can I retake the unit 3 test this Saturday? And so if you emailed me that, and that's fine, I would just set up a testing window for you, and you'd have the entire day. There would still be a time to test whenever you got started. So the other question was asked was, would it be the same test? And remember, the way I build the test is that they're randomly generated. So you would be given the same test, but that doesn't mean you're going to see the same problems. So we'll probably see some of them that are the same, but some of them will be different. And so, yeah, you'll be able to do the test retakes. And so start thinking about that, and don't forget to do that before the quarter is over. Okay, the Unit 6 test was going to be next Wednesday, which is the 30th of September. I'm pushing it back one day to Thursday. That gives us a little bit more time for Unit 6, which I think will be beneficial. That doesn't change much, but again, use the progress check as review as we get closer to that date. I don't know if there's anything else I was going to mention with that particular test. If I think of anything else, I'll say it. The midterm will be the very last day of the quarter, the Friday before the week of fall break. So whatever date that is. Everyone is going to take the midterm, but, and this is a good but, the grade will only be counted if it brings your grade up. So if you're sitting there with a pretty good grade and it brings you down, then it's just going to go in without accounting toward your grade. But if you're kind of trying to bring your grade up, this is a really good opportunity for you to really put in a lot of effort, bring that grade up. So here, between the progress checks, the homeworks, the test retakes, and the midterm, those are 4 ways you can think about bringing your grades up. And last thing, anyone who is currently making a D or an F, I'm going to try and meet with you in the next few days, certainly by next Wednesday. And I'd like to kind of talk with you about what your plan is so that we can get everyone on track for doing well. Okay, that's all kind of the housekeeping stuff. If you have questions about any of that, you can chat me those things, or you can, if you have any questions right now, you can ask. If there are questions, you can bring those up, and you can stick around after class to ask those. So we're going to jump into the very first part of chapter 16, and I'm just asking a basic question. How many vehicles are at your home? And they can be, because 5th hour, people are talking about broken down cars and stuff like that. That's fine. You can count whatever you'd like, and just put that down on this we're going to make a dot plot out of it. All right, make sure you're stacking your dots. I know that some of you don't realize someone's putting a dot down, so if you need to move yours, you can. Okay. We basically have everyone having responded so far. Maybe a few more data points can be put on. Okay. And was that supposed to be a 6 or a 7 right there, just so we know? Okay. There we go. All right, so I think that's pretty good. If we are adding more, we'll figure that out in a second. In fact, I'm going to just be talking about this before we do any calculations, so if you need to add something, you can. So the very first part of chapter 16, if you haven't already read it, of course, that's going to be part of your homework. Read chapter 16. So this is what we call a discrete random variable. And we talked about the term discrete. That means that it only takes on specific values. And in this case, integers. Even though a car might be half broken down, you consider it half of a car, we consider it, added as an integer. So yes, maybe you've got 5 cars, maybe you've got 3. You're not going to have 3.5, 4.5, or anything in between. So it's discrete. It can only take on specific values. It's not always integers. It can maybe be 4, 4.5, 5, like if you're talking about shoe sizes. So anyways, a random variable is a variable that represents a random phenomenon, and its outcome depends on a random event. Now, this might not seem like it applies. So obviously for you, individually, it's not random. You know how many cars you have, and you have the freedom to sell a car or buy a car, right? So it's not random, but what we're saying by random is that if I just took some random person from the street and I tried to predict how many cars they had, it's going to fall into one of these categories. Maybe they're even like 9 cars, you know, but it's a random variable, and we can kind of, we don't know what the outcome is going to be for a random person. So if that's making sense for you, that's where this comes from. Okay, so if we wanted to find the average of this data set, we have to find a weighted average. Now we have an option here. I could just add all these values up. I've got, let's see, we got 7, 12, 13, 14, 15, 16 data points. I could just add up all the data points and divide that by 16. And that's essentially what we're about to do. But what we're going to do is actually find a weighted average. And the way we approach this is that we're going to weigh each outcome by the probability that the random variable will take on that value as its outcome. So, and we're going to jump into the actual calculation in a minute, but right here, there's only one person out of, say, 16 or 18, whatever I said. Let's, 16. Only one person out of 16 has 7 cars. So there's a 1 in 16 probability that 7 is the outcome, whereas 5 people had 3 cars. So there's a 5 in 16 probability that someone has 3 cars. So if I take the actual outcome, multiply it by the probability, that can give me the mean. Okay, and so here's kind of the formula behind it. The average is indeed the mean. It's also called the expected value. So this right here is your expected value. And just a notation comment is that this X right here is your random variable. And we always use capital letters for random variables. That's how we can distinguish them from other things. So if you start seeing capital letters, then you're going to have to immediately think, okay, I'm going to be using rules for random variables, which we'll get into in the next few chapters. Okay. And E of X is expected value. So that's all good. Now we can move on to the calculation, because we're going to use this formula. And this is going to be a little easier for this class. There's fewer data points to work with. It got kind of messy for 5th hour. So I've got 3 right here. I've got 4 right here, 5, and then 1, 1, and 1, and 1. So pretty good. So what we want to do, what this is really saying is sigma, if you recall, means the sum of. So we have lots of different cases here. I've got, really, you might even say this is X sub I and P of X sub I. All right, because that means we have different outcomes that are possible. This is the outcome, and this is the probability of the outcome. So in our cases, the outcomes that matter here are 1 through 7. If we just pretend like the other values don't exist. So I've got the sum of all of these outcomes times their probability. So this is going to be 1 times, because 1 is the outcome right here, and the probability is 3 out of, we decided that's 16, so 3 out of 16. That's a 3. Plus, and it's sigma, so that's why we're adding it all up. The next outcome is 2. 2 times the next probability, 4 out of 16. You could simplify, but it's not probably necessary. Plus, the next outcome is 3 times 5 out of 16. And then so on down the line. So 4 times 1 out of 16, and the next ones will look pretty much the same. So 6 times 1 out of 16, and then lastly we've got plus 7 times 1 out of 16. So this calculation is how we get the expected value. There are ways of doing this using the calculator in a faster way, but we'll talk about that tomorrow. We're going to do the calculations by hand today. And we don't necessarily need to go and calculate this because we're going to do some other examples. I just wanted to set up the equation because this is part of the difficulty of expected value. But, you know, if you understand how we set that up, we could go and calculate it. And we're going to now do it with a more practical example. And I will get rid of all that. So we were using empirical data with all of our values that we added to the dot plot. But here, let's say this is a theoretical probability based on how things are printed out. Okay, so we've got a lottery game. Here are the following payouts and odds. So we've got 1 in 5 probability of 5. I'm not going to read it all. You can see the table there. So I want to come up with the expected value. All right, and so actually I'm going to clear that, move it a little bit over so we have some room. So I want to take all the different outcomes here. And here, a lot of times this is written with X right here and P of X. And so you might have those labels. So the outcomes are 5, 10, 20, 50, and 100. And of course we can see the probability, so I do 1 in 5. So 1/5 plus 1/40th plus 1/100th plus, and we're going to actually do this calculation. So if you know what you're doing, you can start plugging those numbers in because we want to figure out the expected value. And that's what our equation looks like. I will start plugging those values in and we'll make sure we all get the same answer. As soon as someone has found the answer, I don't mind if you want to write that down right here, what your expected value is. Okay, so I got a different value than that. And it's easy to, like I was saying, we're going to learn a faster way of doing this on the calculator tomorrow that's a little more accurate than trying to do this by hand like this. So again, I got a little bit of a different value than that one. Okay, and that's what I ended up getting, 1.52. If you didn't get that, I don't think it's because you don't know what you're doing. I think it's easy to accidentally put something in wrong, like, oh, I accidentally put 4 instead of 40. I forgot to type that 0. So that can happen. Again, we'll try and see other ways of doing this so that's less likely to be the case. Okay, so 152, and a question came up in 5th hour. So like, what does that mean exactly? This is just the average value. And so if we imagine, and there's no way I'm going to write this out, but if we imagine we had 5,000 cases, or the probability distribution, but we showed all 5,000 possible outcomes, well, we're going to have quite a bit of zeros, right? We're going to have a bunch of zeros, 0, 0, 0, dot, 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 dot. And then at a certain point, I'm going to have 5 as an outcome. So I might have 5, and a fifth of the outcomes are going to be worth 5. And then I'm going to have maybe a few 10s and a 40th of those, so less of the 40s, and then 20s, maybe a fewer of those, 50s. And so the dot dot represents that I might have multiple outcomes that way. But then I get to 100, only one person in 5,000 is going to have $100. So then I just do this as a giant addition problem. I add all that up and I get some number, and then I divide it by 5,000. So whatever this value is going to be, some X value divided by 5,000, and that number will be 1.52. So this is, especially when you're dealing with probabilities rather than like a data set like we started with. But if you're looking at probabilities, it's the weighted average. The expected value is the kind of straightforward, simple way of finding the mean. If you have 10 data points, of course, add them up and divide by 10. That's easier to do. So anyways, that's kind of what this means, just in case it was a little bit unclear. All right. Now, I should mention it's fine that we don't have it in our table, and a lot of times that's the case, but there should be another outcome here, which is $0, because of course most tickets aren't going to win. I'm not going to figure out the probability. It's the complement of what everything else is added up. So something out of 5,000. We don't care because it doesn't really affect our calculation. If we added this in plus 0 times that probability, then it's all going to cancel out to 0 anyway. Okay, so a few little random things there, but now we can kind of answer these questions. If it cost $1 to play this game, would you play it?
Yeah.
Yeah.
Okay. Yeah. Now, I guess we have to be a little careful about this. What this is saying is that over the long run, we should expect to average $1.52 in winnings. Sorry, in income. That's not necessarily our winnings, but we should expect $1.52 in our revenue side for every time we play on average. So if it only costs $1, well then that 152 minus $1 that we had to spend means that every single game we play, our actual net income is going to be 52 cents. Of course, we also need to interpret this the right way. If I played this one time, I'm either going to win 0, 5, 10, 20, 50, or $100. Those are my only outcomes. But if I bought 1 million of these tickets and they all had these odds, then I would win 1 million times 52 cents. And so that's pretty good. So if you have a positive expected value, this is a positive expected value, that makes it a good bet. If it was $2, what would our what would our payout be? Or maybe I'll just go back to the original question here. If it cost $2 to play this game, would you play it?
No.
No. All right. And why would we not want to play this game at $2?
Because you're going to lose an average of like 48 cents.
There it is, yeah. So that 152 minus the 2 that you had to spend to play makes it a negative 0.48. Now, this is something that people use in the real world to figure out if they're going to play and participate in a certain lottery, because every once in a while, there is a lottery with a positive expected value. And I should add a caveat to this. If this expected value was $1 million instead of 100, that would change our odds. That would change our expected value greatly, and it would look positive. But just as a caveat, if you're planning on using this to settle whether you should gamble on something or not, if there's only one outcome that skews the expected value, kind of like an outlier, then you have to take that into account, and maybe expected value has limitations. Anyways, that was a brief aside. Negative expected value means it's a bad bet. Positive means it's a good bet, generally speaking. How much would you be willing to pay to play this game?
No more than $1.52.
There you go. Now, this question is a subjective one. So in one sense, there's no right answer. If you love losing money, I guess you could say I'd be willing to pay any amount because I love lottery tickets. But in general, mathematically, what you'd say is $1.52 is the maximum I'd be willing to pay so that I could break even. But of course, subjectively, you might say, I don't think I'd pay more than $1 because, you know, if I paid $1.40 and only won 12 cents on average, that's not really worth my time. So anyways, as long as you're not going above 152, that mathematically, that's kind of the way we approach it. All right. Let's clear all this. We're going to go through just a few practice problems from the book. And I actually don't need to spend much time with number 2. in fact, I'm not even sure that we're going to spend any time because we're going to do these calculations. But you can see it's just they give you a probability to, model, and now you need to go through and find out the expected value. The one thing I will say, and we're going to do this ourselves, but it's always a good idea to make sure that this probability distribution is a good one. So if I add this up, 0.1 plus 0.2 plus 0.5 plus 0.2 is 1.0. So good, it adds up to 100%. It has to add up that way or else it's, you can't really use expected value at that point. Okay, so you guys can figure that one out, I imagine. Okay, you roll a die. If it comes up 6, you win $100. If not, you get to roll again. If you get a 6 the second time, you win $50. If not, you lose. Create a probability model for the amount you win. So this is the hard part of this problem, is creating the probability model. So I'm going to create a model this way. And I have my event and the probability of the event. And now we need to think, what are the possible outcomes here? And I have 3 outcomes. I could win $100, I could win $50, I could win no dollars. So that's what I'll write. $100, I've got $50, and I've got no dollars. And to see where that comes from, I could win 100, 50, or lose, and we presume that means you just lose your money. Okay, now the probability, we have to go back to our last unit, kind of figure this out. If we roll a 6, on the first roll we get $100. What's the probability of that happening? And anyone can say it.
1 out of 6.
There it is, 1 out of 6. Now the second time, what's the probability of getting a 50? Sorry, what's the probability of winning $50, I should say? How do we find that?
We do would it be like 5 out of 6 times 1 out of 6?
You got it. So just to put it in probability language, I should say maybe right here, this is the probability of getting a 6. Right here, that's what we found. But now we want to find the probability of getting a 6, given that we did not get a 6 the first time, which is the probability of not getting a 6. Wait, no, I'm sorry. I said that wrong the first time. I was like, that doesn't look right. There's no conditional probability when they're independent. Okay, sorry about that. It's the probability, if I can write and think at the same time, of not getting a 6 and getting a 6. So you said it right, Sam. So not getting a 6 is that 5 and 6 probability. If getting a 6 is 1 and 6, then not getting it, it's the other part. And not getting and getting a 6 the second time around is 1 and 6. All right, if I'm not confusing you enough right now, this is the calculation we're doing, and we can find this is 5 out of 36. Okay, which means the other probability is after 2 rolls, we don't get a 6 either way. So that's a probability of not getting a 6 and not getting a 6. So what's our calculation on that one?
5 out of 6 times 5 out of 6.
All right. And this is our check to make sure we did everything right. I got 25 out of 36. Well, let's go back across and add everything up to make sure we got 36 out of 36. And to do this, of course, we're going to want to change this from 1/6 to the equivalent 6 out of 36. All right, and when we add that up, it looks like we get 36 out of 36. We did this probability model correctly. So now we've got these outcomes. Sorry, those probabilities with these outcomes attached. So my expected value, the expected amount that we're going to win is going to be, we're going to just set this up and then we're going to move on. We're not going to actually calculate this out. So it'd be that 100 outcome times the 1 in 6 probability that it will happen, plus 50 as an outcome times the 5 out of 36, and then 0 as an outcome times 25 out of 36. Actually, let's go ahead and do this calculation just to see if that turns out to be. Or easy to make a mistake, I should say. All right, so 2361. There you go. There's our expected amount we'll win. So just going to that last question again, how much would you be willing to pay to play this game?
$23.61.
Okay. And Zayden, earlier I saw your comment that for that last example, you would only be willing to go to a certain level just so you can have higher profit. So, you know, your subjective line might, what might your subjective line be for this one, Zayden?
To be honest, I wouldn't play this game at all.
That's fair. That's fair. Because one thing to keep in mind, you're playing this game many times to win on average 2361 each time. But you are going to lose 25 out of 36 times. You're going to lose a lot. And you're counting on that law of large numbers to average you out to 2361. All right, so, and you have to trust statistics at this point. But yeah, you might draw this line. As long as it's less than 2361, you're good. All right, we can move ahead because really the hard part is creating these probability models. So let's look at this one. This one gets a little more fun. Okay. We've got a carnival game that offers a $100 cash prize for anyone who can break a balloon by throwing a dart at it. Costs $5 to play. You're willing to spend up to $20 trying to win. You estimate that you have about a 10% chance of hitting the balloon on any throw. I don't have the questions down here, but I think the questions are basically the same as the last one we did. So what's the probability model? What's the expected value? How much would you be willing to pay? Okay, now keep in mind, well, it already tells us it's $5 to play. Keep in mind that as soon as you win, you're done. You're not gonna spend $20 no matter what. That depends on if you hit the target or not. So as we go through and we're creating, I'm not gonna worry about this $100 yet. We're gonna come back to that later. But I've got a few outcomes that might happen. What's the most basic outcome that could happen?
Do you hit it
The first try.
Hit it on the first try. So I will put H for a hit, and I'm done. I've won. Let's not worry about the probabilities just yet. I'll give myself a little more room. What is the next simplest possibility?
Hitting it on the second try.
There you go. I might hit it on the first. I might hit it on the second, which would be a miss and a hit. I might hit it on the third, right? I might hit it on the fourth. Now, because it's $5 to play and you're going to spend $20, you only have 4 throws. So you might hit it on the fourth. Of course, what also might happen?
You miss all of them.
You miss all 4 times and you don't get to impress your date. All right. So we'll worry about the money again at the end. But here are the possible outcomes. And we know that this has to equal 100% of all the probabilities. So hitting it on the first time, we know it's 10%. All right, so this is a probability of, I'm going to add actually another row right here. It's going to be probability both times, but I'm just going to make it look a little neater, perhaps. So this is going to be the probability of a hit. What's the next one a probability of?
Probability of a miss and a hit.
There you go. So it's probability of a miss and a hit. And the next one?
Miss and hit.
You got it. All right, now we know what to do. Miss and miss and miss and hit. And of course now it's miss and miss and miss and miss. Okay, probability of a hit is given right here. Probability of a hit is 0.1, which means the probability of a miss is the complement is 0.9. All right, now we can just plug this in. They're all independent. We can just multiply them together with the multiplication rule. Probability of a hit, 0.1. Probability of miss and hit, well, 0.9 times 0.1. All right, and so on. I'm not going to write that out, but now we can actually do the math. So this is the probability here. This one would be 0.09. See if you can fill in the rest of this table with the probabilities. So there it is. We've done all the difficult part of this problem, but we can calculate the actual probabilities, or the actual expected value. Now here's what we need to remember. It's worth talking about what the actual outcomes are. So I'm going to come back and add one more row, because there's one other level of just something we need to think about. If I hit on the first try, what are my winnings?
$100.
$100. And here's what we need to keep in mind. Now we're going to factor in the cost that it costs $5 to play.
$95.
There it is, 95. And the reason we're doing it here is because in the previous examples, we were only doing something once. So I could kind of, after the fact, say, oh, okay, well, there's the cost involved. But here we're playing potentially up to 4 times. So now I need to factor in the cost of doing it each time. So what are my winnings for hitting it the second time?
$90.
There we go. We can see it just goes down from there. The third time, 85, then 80. And then, of course, what are my winnings if I miss all 4 times?
0.
Less than 0.
-20.
There it is. So we're actually spending the money, but not getting anything as a result. So now these 2 multiplied together plus these 2 multiplied together, and here's the expected value calculation. And of course, if we added this up, I'll go ahead and tell you these are all correct. This is 7.0729, but if we add all those up, it's going to be 100%. So we did this right. But now if we do the multiplication, add those up, we're going to get our expected value from this game. And we're going to see, if we do that, I'm actually going to move ahead. But if we do that, you might see, is this a good bet? It costs $5. Is our expected winning positive or negative? So again, imagining you're going to play multiple times. All right. So there you go. Any questions on this one? Right. Let's look at one more. Okay, I gotta erase all this stuff from here. So this last one, we've got a man buys a racehorse for $20,000 and he's gonna put it in 2 races. He plans to sell the horse afterwards and hope to make a profit. If the horse wins both races, its value will jump to $100,000, $50,000 if it only wins one, only worth $10,000 if it loses. You can see the probabilities for each race and they're independent. So we're gonna find the expected profit. Now this is the actual expected value. This is our E of X, or the mean. But we have to, of course, set up our probability model in order to find that. So let's kind of think through this. All right, what is the first outcome that you think of?
Wins both races.
All right, wins the first race, wins the second race. I like it. Next one.
Wins one.
Wins one of them. Okay, so let's just say he wins the first race, loses the second. What other possibility do we have?
Loses the first one, wins the second.
There it is. And we consider these differently because we actually have 4 possibilities. So we want to kind of factor that in. Of course, that means the last one is he loses both. I'm sure everyone can see that. So figure out the probabilities here. And we can just kind of maybe do this quickly. I'm just going to put what the probabilities are. The probability of winning the first is 0.2. The probability of winning the second is 0.3. And that means the probability of losing the first is the complement. And the probability of losing the second is the complement. Now, keep in mind, for all of these, we're dealing with 2 outcomes. You win or you lose. So it's success or fail. And we're kind of keeping that in mind. So that kind of simplifies everything. So now we've got this, we can kind of plug these in. I'm not going to write it out formally. If this doesn't make sense, you can stick around. And hopefully you know what you're doing. You can fill this out on your own paper. You don't need to see what I'm doing. But if these numbers, you're not sure where we're getting them from, we can kind of go through it a little more. And of course, at the end, make sure it adds up to 100%. And as you guys are getting them, you can feel free to fill in this table. Or you can just do it kind of underneath what all these equal. Okay, and that looks looking good. If we add this up across, we should count up to 100%. Make sure that you guys agree with that. And now we can, well, we can't quite find this yet because we need to make sure that we kind of, I'll add this other row above. We need to see the actual outcomes in terms of winnings. So in the first case, winning both races, what are the profits?
100,000.
Not 100,000.
80,000.
There it is. So yeah, it's the 100,000. And then how do we get the 80,000?
Minus the amount he bought the horse for.
There it is. There's that sunken cost in the horse. So yeah, there we go. 80,000, which means for winning one race is going to be what will the profits be for one win?
30,000.
There we go. And it doesn't matter in our scenario whether this horse wins the first or the second race. And then our profits for losing both races is
Negative 20,000.
negative $20,000. Well, yeah. No, wait.
Negative 10,000.
Yeah, there we go. Because you will be able to get $10,000 back from selling the horse, but not 20,000. Or but you're not going to get the full 20,000 back. So yeah, you're going to lose 10,000. There we go. So now it's, these values multiplied together. You know the expected value, hopefully by now. So we can figure out expected value. In fact, I'm just going to leave it without writing out the equation. I encourage you to, but I will leave that up there. We can figure out our expected profit. So there we go. Good job. 10,600. That's what I got. So if two people got it, it must be correct, right? But I'm sure most people are coming up with that same answer. There you go. Expected value or expected profit from this. So just to reiterate one last time, right before we're done, this means if you did this every year of your life and you did this with like multiple horses per year. So let's say you did this hundreds of times, maybe even thousands of times over the course of your life, you would expect to get $10,600 per horse. And that doesn't mean, but in reality, each horse that you get, there's a 56% probability that you're gonna lose $10,000 on it. So you're counting on those big wins to counterbalance the losses. And there you go. So it's really important to remember with expected value, we're talking about large numbers of trials to get that average value. Okay, if you have questions on this, of course, please stick around. There are a few things to mention here. I'll get rid of this so there's nothing in the way. Read chapter 16 if you haven't done that yet. For today's class page, when you go to the September 23rd page, September 23rd class, you'll see a video that I posted from, it's the same source that I gave for a video last week, and I forgot the name of the group that puts it out. But anyways, this is just a good way of kind of thinking about random variables, and it gives some interesting scenarios. Not much homework tonight, and they all look like what we just did in class today. If you have questions, you can stick around. That is it for class today. And remember, the test is not until next Thursday, so we're going to try and space this out a little bit more.